everyone, welcome back to the latest lecture session. In the context of wastewater treatment, we were talking about the last aspect that's relevant to us, which is killing or inactivating the pathogens, the disease causing or those microorganisms which are capable of causing disease, let's say, right? So there are different disinfecting methods or agents, pardon me, and one common aspect among all the chemical agents is that they are oxidizing agents. But oxidizing agents, different levels of efficacy and different levels of effectiveness against different pathogens, let's say. In that context, we saw that we typically apply chlorine. Chlorine can be applied as Cl2 itself or NaOCl and such. So typically we are trying to form HOCl, OCl minus, right? Will always be in equilibrium with HOCl whenever you form HOCl, right? Because HOCl will dissociate to form H plus and OCl minus. HOCl is an acid. Depending upon the pH, it will be in equilibrium with H plus and OCl minus. We will look at this later again. So to look at the efficacy, we looked at this particular graph or piece of information here. We saw that HOCl requires much lesser CT than OCl minus or NH2Cl, thus it is much more effective to kill the relevant pathogen. Here the pathogen of interest is E. coli, let us see, right. So move on. Here we see the other aspect, as in we are just looking at HOCl in the context of its effectiveness against different kinds of pathogens. So virus, E. coli, virus. So we see that for different types of virus, different contact times are required, and you see that the range is considerable. 100-minute contact time is a lot. So obviously you need to look at what it is that you are trying to achieve. So for wastewater treatment, disinfection relevant standards are different. For water treatment, standards are much more stringent, obviously. In the context of wastewater treatment, it is relatively different. But I wanted to point out that there is no such case as if there is one dose at which almost all the viruses or pathogens are going to be inactivated. So that is what again we saw here. So again, typically in India, we look at chlorination, right, free chlorine, but its effectiveness against Giardia and Cryptosporidium is relatively limited. Okay, Cryptosporidium, okay, we have some Microsporidium listed here. But again, the effectiveness is pretty limited. And why are they of interest? Because they can cause diarrhea, which is one of the leading causes of diseases, not diseases, deaths in India. So here we have another table from Metcalfe and Eddy, right, Metcalfe and Eddy. And here we have the different disinfectants. The units here are milligrams per liter, so concentration, mass per volume and time. So these are CT values. Only for UV radiation we have different values because its intensity into time, let us say, right. So that is what we have to look at. So let us see what else we have. Here we have different types of microorganisms of interest. Total coliform. Why or when did we come across total coliform? I think we looked at this in the context of water quality. Total coliform will give us an idea about the quality of the water, but in what sense? In the sense that they are indicator organisms for microorganisms or pathogens that can or live in the intestines of warm-blooded animals. So it will give us an idea about contamination due to human feces, let us see. But total coliform is having different sets of coliform. If we want to look at feces contamination specifically, we look at fecal coliform, but in general total coliform is also fine for wastewater, I guess, right. And here we have coefficient of lethality, okay, to the base 10, but again we will not look at that in detail, just let us look at the numbers for now. So for total coliform, we see that ozone and UV are doing pretty well, but chloramines in general, I think we also looked at this graph. Okay, combined chlorine, you need a lot of time with respect to combined chlorine, and also they are relatively limited in effectiveness, and also that is what you see here, right. Much more time and concentration are required, let us see. So that is what you see, it is consistently faring poorly, and these are the protozoa or pathogens that I talked about, Cryptosporidium and Giardia, right. So with respect to chlorine, which is widely used, it does well against viruses. Okay, coliform, we don't discuss that a lot, but does not do well against protozoa like Cryptosporidium and Giardia. So that's what you see here, right. So that's of concern to us, but it does well against viruses. Chlorine dioxide, okay, decent effectiveness, but again, it's not great though. That's what you see, decent but not great. It's not as poor as chloramine though. But with respect to ozone, you see that in general it's obviously much better than all the other oxidizing agents. UV again, but with respect to virus, it has limited, what do we say, looks like it has limited effectiveness, but again it depends on the kind of virus and the type of RNA that it has. But with respect to fecal coliform and Cryptosporidium and Giardia, you see that it does pretty well. So the choice will depend upon what you are trying to achieve, what's prevalent in that waste water or water, and so on and so forth. But obviously there is no one particular agent that's effective against everything. But in general, if you are thinking about viruses and you don't have a lot of money to spend, obviously chlorine, I guess, but again this is in water. Why I want to mention this here is, you would have seen, I mean, this is the age of or at least this year is 2020, and people spraying HOCl or chlorine dioxide, ClO2 or a solution of HOCl or OCl minus. They put it in a tanker, put it like as if it's an insecticide spray tank, put it inside an insecticide spray tank, and then they spray it. You would have seen that. But again, I mean, think of how dumb it is. Firstly, you don't know when he prepared the solution, it's going to decay. The oxidizing agent, the capacity or the effectiveness will decay. Typically, they would have used ClO2 or HOCl and OCl minus or some form of chlorine. It's going to decay, it's an oxidizing agent. And then nextly, what is it that we are trying to kill? Let's say this is air, the air, and I have what do we say, corona positive, and I have breathed in this air and I leave it. When they say disinfection, what can you really do? Can you, what do we say, clean this, all the air in this, what do we say, 10 by 10 room? It's not feasible. Even when you spray, you are just throwing out mist. Will that go and, what do we say, come in contact with the particular virus and then oxidize it? No, it's not going to happen. But why do people do that? Well, people don't listen to science. People do that for a lot of reasons, typically to pacify the population, to show that people are doing, or the people in charge are doing something. For example, a more effective way would be, to see the areas that I have been touching or coming in contact, use a solvent and then wipe those areas, let's say the doorknob and such. But no, they come and spray. With the spray, you don't really, what do we say, catch the entire area, or the oxidant is limited to only those droplets. So again, people act in weird ways. I wanted to mention that aspect here. So let's move on, come back. So just to understand the kind of doses that are required, here we have the disinfectant. Okay, disinfectant is listed against the kinds of pathogens that we want to kill, different types of protozoa that can lead to or will lead to diarrheal diseases or diarrhea, and virus and bacteria, let's say. And here we have different levels of inactivation. So 4 log meaning 99.99% removal, 99.9% removal and such. So it depends on whether it's used for wastewater or for water. So let's not go into that right now. So with respect to virus, we know that chlorine is decently effective. So even at relatively low dose, it's milligram per liter minutes, right? So this is CT value. The units are CT values. You see that you can kill the viruses. Chloramine, not very effective, and that's why you see a lot of or very high CT values required. And with respect to ozone, very effective or remarkably strong oxidizing agent. So you see remarkably less CT values, right? And UV2, I guess we see this. And in the context of the Cryptosporidium or the protozoa, both the protozoa, we see that chlorine not really effective. You see that it's remarkably high value of CT that you require. But with respect to ozone and UV, yes, you can achieve that. Same case with respect to protozoa, let's see, right? So that's something to give you an idea about. So in general, if we are trying to kill only viruses, as you can see, that is fine. But if you are trying to look at diarrheal diseases, just adding chlorine at the usual amounts to kill virus will be of no use. So that's something to keep in mind, right? So in general, again with bacteria we will not go there, but I wanted to compare this so that you can look at the actual, or get an idea about the kind of values that are required. So this is one of the reasons why I guess some of our water distribution networks still do not cut down on the relevant transmission of protozoa or such, right? So that's something to keep in mind. So redox reactions, I wanted to discuss this because we have been talking a lot about oxidizing agent and so on and so forth. Oxidizing agent, what is it? It's an electron acceptor. But electrons don't float around freely, not in the solution, not in the air. So unlike H plus, they don't float around, so it has to be a direct collision between compound A and compound B for the electron to be transferred. So if I am an electron acceptor, I also need an electron donor. Only then will the relevant reaction go through. So we are going to have an electron donor. So oxidizing agent or oxidant and reducing agent, let's say, right? So let's look at that. So in redox reactions, we have one or more electrons being transferred from one element to the other. It's a transfer of electrons. Oxidation is the loss of electrons. When we say a compound is being oxidized, let's say it means that there has been a loss of electrons. And when it's reduction, it's a gain of electron. Keep in mind that here we say it's an oxidant when it's an electron acceptor. So here we have O3, Cl2, HOCl and so on and so forth. Electron donor is a reducing agent, a reductant. A reductant will reduce the other compound while being oxidized, let's say, right? So that's one aspect to consider. So that's what we have to look at. But oxidation and reduction, they don't happen, what do we say, independent of each other. When we are talking about oxidation, certainly reduction will happen. Why? Because you can't have, what do we say, electrons only going in one direction. As in, if I need have an electron donor, right, I need an electron acceptor also. So only when you have both oxidation and reduction occurring will you have redox reactions, let's say. So it's not as if oxidation will occur, what do we say, in or being independently of reduction. But when do we say oxidation? For example, we were talking about organic compounds. So I am talking about oxidation there. So why am I calling it oxidation? Because my compound of interest, which is the wastewater or the BOD or the organic content, is being oxidized. So that's why I am calling it as oxidation. But obviously for that I need an electron acceptor, right, which is oxygen. Oxygen is taking the electron from the organic matter and it's being reduced, let's say. Again, so let's not go there. If you are confused, you can just look at it twice. But in general, if I gain an electron has a negative charge. So the charge on that particular element will decrease. So reduction in the charge. Maybe that's way you can try to understand it, right? Let's move forward. So chlorine gas, once I bubble this chlorine gas or dissolve that in water, it will go ahead and form HOCl and HCl. HCl will typically never stay as HCl, it will go to, though it can be like this, H plus plus Cl minus. HCl being a very strong acid will go to H plus and Cl minus and stay like that always. Why? We will look at that later. But what will happen to this HOCl? Unlike HCl, it's not a strong acid. We will see what it means when we say it's a strong acid or a weak acid. So HOCl will be in equilibrium with OCl minus and H plus. So this can go this way or this way, let's say. Yes, but in general HCl will always dissociate. But with HOCl we know that it will be in equilibrium with OCl minus. So it's not a very strong acid, but it's a strong oxidizing agent. HOCl is a strong oxidizing agent. We will look at these aspects. So here we have an acid HOCl and a base OCl minus. What is an acid? Acid is one which can give out a proton. What is an OCl base, right? What is a base? What is a base? A base is one which can, what do we say, accept H plus, let's say, right? So that's one aspect. So pKa, which will give me an idea about how strong the acid is or not, is called the acid dissociation constant. It's called the acid dissociation constant, right. So that's what we have. How or where will I get that from? Let me see that. Okay, I have other aspects to mention, some terms here. So we have acid. HOCl is an acid. So what's the property of an acid? It's a proton donor, as in it can give out a proton, H plus, right. And what is OCl minus? It's a base. And what is its property? It is can take up a proton, so it's a proton acceptor, let's see. So that's something to keep in mind. Acid donor or something that can donate the acid, and thus by releasing H plus, you are going to bring down the pH of the solution. So add an acid, if it can dissociate and release the H plus, it will bring down the pH of the solution. OCl minus, on the other hand, by taking up the H plus or removing H plus from my solution, will increase the pH. What is pH? Okay, I already have it here. pH is the negative log activity of H plus, but discussion about activity is, I guess, a bit too advanced for this course. So we will assume that activity can be approximated by concentration of the relevant compound or element here, right, or ion here, pardon me. So what do we have here? We see that pH equal to negative log H plus. So if I increase H plus, which is the case when I add an acid, you will see that my pH will decrease. But by adding a base, if I remove H plus, right, or I decrease H plus, what will happen? The pH will increase. So when the pH decreases, it's called, the solution is called acidic, and when the pH increases, the solution is called basic. But the reference is 7. So pH 7, we say that the water is neutral. Why is that? Range of H plus 0 to 14, you know, H plus is equal to 10 to the power of minus 7. So then we say that the water is neutral. So our pH is equal to 7, let's see. So in this range it's basic, in this range it's acidic, let's see. So general or some aspects. So two aspects here we need to understand: equilibrium, acid base equilibrium. When we say equilibrium, we are talking about the state of the system. Let me not get too technical, but again, state of the system, to use layman's terms, it will tell me how far the system can go, let's see. And in that context, kinetics will tell me how fast is the system going, let's see. Yes, so kinetics will tell me how fast the system is going or the process is going, and equilibrium will tell me, given enough time for the relevant temperature and pressure, how far, right, the state can the system go. So in general, acid base reactions, the kinetics are very fast. That is why almost always acid base equilibrium is achieved. This is not the case for redox reactions. For example, you saw in the wastewater, what we say, relevant aspects with respect to activated sludge process, we are giving it considerable time, it meaning the redox reaction of organic matter being oxidized by oxygen, that's a redox process. Their kinetics is relatively slow, that's why obviously time comes into the picture. But here in acid base, you know, equilibrium is always reached. Why? Kinetics is pretty fast, let's see. So that's something to keep in mind. So acid base equilibrium, we'll just look at that because we want to understand this concept of HOCl, OCl minus, because we know that HOCl is much more stronger oxidizing agent compared to OCl minus. Here HOCl is an acid and also a strong oxidizing agent. So equilibrium constant, for example, we spoke about pKa, acid dissociation constant, and that it gives us an idea about the strength of the acid. Let's see what it is or how it comes about. For any reaction, or let me say for this reaction of acid dissociation into H plus and its deprotonated form, which is the base, you will have a equilibrium constant, capital K. That will give me an idea about, or is be depend upon, this is equilibrium constant. So it's only applicable when the system is at equilibrium. B is equal to activity of H plus, activity of A minus by activity of the reactants raised to their stoichiometric coefficients. Because the reactant is only HA, I am going to have only HA here. In this class, we are not going to use activities. So, we are going to approximate it by concentration of H plus, concentration of A minus by concentration of HA, right. So, if it was 2 HA, then it would have been HA square, but again that is not what we are looking at. The stoichiometric quotient is only 1, so that is why it is raised to 1. Same case with H plus and A minus, let us see, right. So, this is called the equilibrium constant. It will tell me once the system is at equilibrium, what is the situation or scenario going to look like, let us say. Given enough time for the system to reach equilibrium, what will it look like? So, this is the equilibrium constant. So, pKa similar to pH, pH is minus log concentration of H plus. So, pK is also equal to minus log Ka. So, let us see how we can get that. Do I have a blank side here? Yes, I do. So, what do I have here? I have HA, and this will be in equilibrium with its deprotonated form, the base and the proton. Why am I saying deprotonated? Because it is releasing its proton. So, for this the equilibrium constant K is, or Ka is, concentration of H plus products by the reactants, right. So, if I take the logarithm on both the sides, log Ka will be equal to log H plus log A minus by log HA, not log, by HA. I am not taking this out because I want to leave it as a ratio. So, if I swap both these terms, this will become minus log H plus, this will become minus log Ka, but minus log H plus is pH. So, I know that pH will be dependent upon minus log Ka is pKa, which is the acid dissociation constant, plus log of A minus by HA. So, the ratio of, let us say, this OCl minus and HOCl, which I am concerned about. Why am I concerned about? I want more HOCl because that is a stronger oxidizing agent, right. So, that is something to keep in mind. Will be dependent upon the constant, which is the dependent upon Ka, or the acid dissociation constant, and the pH of the solution. So, this is a constant. I know that for this particular system of HOCl and OCl minus, the pKa is 7.5, right. So, I know this. So, depending on the pH, I can calculate the ratio of A minus and HA. And also, if I plot this on a graph, I can see how the system is going to behave. Do I have a graph here? Yes, I have this graph here. So, what do I have on this x axis? I have the pH. As we mentioned, the pKa will be 7.5, we will come back to that. And on the y axis, I have the concentration, let us see. Okay, and let us say I initially added in this example, let us say assume that initially I added HOCl naught at a case when the pH is pretty low. Okay, I saw to it that HOCl naught is, let us say, this is molar concentration. So, 0.001 molar equal to 1 millimolar, right, and let us say this pH was at 2. Okay, what do we see? We see that most of it is as HOCl itself and little OCl minus. And if I start increasing the pH by adding any base, let us say OH minus. So, what is going to happen? Until it reaches a particular pH which is around 6.5, as you can see, there is not going to be, not 6.5, 5.5, there is not going to be much change in HOCl, everything is going to stay as HOCl. But as I keep increasing the pH, we see that the concentration of HOCl is decreasing, but simultaneously the concentration of OCl minus is increasing. Note that the total OCl total, which I am representing as HOCl plus OCl minus, is still the same, which is 1 millimolar. It is only that whatever was only present as HOCl now is present in both forms of HOCl and OCl minus. As HOCl is decreasing, OCl minus is increasing. At a particular point, both HOCl and OCl minus concentration are the same, and let us mark that here. Okay, it did not come out well, so somewhere out here. and as I keep increasing it further, OCl minus, it meaning as I keep increasing the pH further, we see that this particular OCl minus concentration keeps increasing and HOCl keeps decreasing until after a certain pH most of it is only present as OCl minus. So, how is this happening? Let us look at what we have or how we came out with this. So, this equation that we derived earlier, this is called the Henderson-Hasselbalch equation, Henderson-Hasselbalch equation, right. So, first things first, when is the concentration of A minus and HA going to be equal? As in, what is this point at which the concentration of HOCl was equal to the concentration of OCl minus? What is this point? As you can see here, the only time when A minus will be equal to HA is when pH is equal to pKa. So, that is what you see. So, when pH of the solution is equal to the pKa of the acid, and the pKa of this particular acid, as I told you, was 7.5 or around 7.5 Na. pKa is equal to 7.5, you will see that when the pH is equal to 7.5, meaning it is equal to pKa, we will see that as predicted by our equation, both the base and the acid, or the deprotonated and protonated forms, are going to be at the same concentration. So, why was I calling HOCl not a strong acid, but why was I calling HCl a strong acid? Let us look at this. For example, for HCl the pKa is negative, or for example, for purposes of illustration take it to be 0.1, and for HOCl the pKa was 7.5. HOCl OCl minus, the pKa was 7.5. For HCl and Cl minus, the pKa was 0.1. Let me try to draw this graph with HCl Cl minus. So, 0, 14. So, what does this mean if it is 0.1? It means that for almost all the range of pH, as soon as I add HCl, it is going to deprotonate and stay as Cl minus, meaning it will almost always give out the H plus. So, at any pH it will give out its H plus, meaning it is a very strong acid. Please note that pK is not 0.1, it is negative or less than 0. So, at all practical pH of water, whenever you add acid, HCl will always dissociate to give H plus and Cl minus. So, thereby decreasing the pH of the water, but that is not the case with HOCl. We will see that particular information too here. Let us see. Let me try to find another. For HOCl, I know that the pKa is around somewhere here. So, for most of the range, the HOCl will be something like this, and this is HOCl, right. And let me try another color. So, only at this point will it be equal OCl minus. So, this point is 7.5. So, as we see, let us say at pH of 3, all the HOCl is staying as HOCl, right. So, that is what we also see here. Let us say at pH 3, pH 4, maybe even pH 5, what is it staying as? HOCl is staying as HOCl, it is not giving out its H plus. So, it will not affect the pH. So, that is something to keep in mind. So, by looking at the pKa, we can tell whether it is a strong acid or a weak acid. Though I digressed, I think it is relevant in this context. Why is that? Because 7.5 is the pKa of this HOCl and OCl minus. And why am I concerned about that? Because HOCl is a much stronger oxidizing agent than OCl minus. So, if I can tweak the pKa, not pH such that I have more of the HOCl, so obviously I will have a greater disinfection capacity in my particular disinfecting tank. So, that is one aspect to consider. So, let us move on. Acid base equilibrium, I guess we just covered most of that aspect. So, another aspect to consider is that pH is equal to pKa plus log of the deprotonated form by the protonated form, right. So, I know that the pKa for my system is 7.5, right, and it is A minus by HA, and let us say if the pH is 6.5, right, what will this turn out to be? Log of OCl minus by HOCl will be equal to 6.5 minus 7.5 is minus 1. So, OCl minus by HOCl will be equal to 10 power minus 1 or 1 by 10, right. Logarithm, I take the 10 logarithm to the base 10. So, I take it up 10 to the power of minus 1 or 1 by 10. So, at pH of 6.5 you see that most of the solution will stay as HOCl, but at the pH of 8.5, which is 1 unit greater than 7.5, this situation will be reversed. At that place or at that pH, most of it will be present as OCl minus. So, you see the key role that pH plays, and that is why we had to look at that Henderson-Hasselbalch equation, right. So, let me move on. So, we looked at addition of Cl2. We can also get this OCl minus in different forms. It can be added as CaOCl2 solid or NaOCl a liquid, let us see, and then you can change the pH so that you have enough HOCl. And as we discussed, right. So, again different forms of oxidizing agent addition. So, chloramines, these are what we call as combined chlorines. These are in general effective against bacterial what do we say, or effective for bacterial disinfection, let us see. They form HOCl, they form as HOCl reacts with ammonia. These are the combined, not these are the combined chlorines that we were talking about, chloramines. So, these are also sometimes added, but not a lot. So, again HOCl reacting with NH3 gets you these monochloramines or dichloramines, but we will look at that later. But we saw that their effectiveness against viruses and the protozoa was remarkably low. So, chloramines are longer lasting, so they can be used as a residual disinfecting agent. So, if you do not want to, what do we say, have a lot of them added initially, chloramines, but you can use that as a residual disinfecting agent, let us say, right. That is why we say they contribute to chlorine residual, right. Let us move back to that or come back to that later. So, we discussed this briefly, disinfection byproducts, as in when we add Cl2 or I guess chloramines 2 in a way, or HOCl and OCl minus, you can form these toxic byproducts which are called disinfection byproducts. Let us look at that briefly before we end today's session. How are they formed? For example, you have this Yamuna, it is pretty polluted downstream of Delhi. Even in other places when it is not polluted due to human reasons or causes, you are going to have water coming in contact with dead leaves, dead aquatic life or dead plants and such. So, these leaves, they are again organic matter, right, everything, life, cells are organic matter. So, they change phase or they leach into the water. So, now you have organic matter dissolved in the water. So, this is called natural organic matter, and depending on the size, it is also referred to as dissolved organic matter, let us see. And this natural organic matter in water reacts with disinfectant, especially chlorine, and forms disinfection byproducts. But I am out of time, so I will continue this in the next session, and as usual I thank you for your patience.